Thanks, Melinda. It's a pleasure to be here. So I'm sure this area has become so hot. I'm sure most people in this room have already seen some flavor of what I'm going to show next. As I call these decision time attacks. Conventionally, they're called adversarial examples. If you have heard anything at all about adversarial examples, you have seen the panda image, which is classified as a panda by, say, state-of-the-art deep neural network. And you add small adversarial noise, much smaller than what you see here. It's amplified fairly significantly. You still see a panda as a human, but the neural network sees something completely different, in this case, a gibbon. And so this particular example accounts for an enormous amount of research on this particular topic. Okay, I'm not going to be interested in classifying pandas correctly, because I think that confusing pandas for gibbons may be somewhat important, but of somewhat peripheral relevance to society. I think a higher order issue is when you classify stop signs as gibbons. Or what I'm going to start with is classifying malware. It's a special case of these kinds of attacks that are called evasion attacks. You have malicious PDF, say, okay, and you add some adversarial examples that have very different forms. There's no pixels in PDFs. You're modifying the actual files themselves. For example, there's variants of attacks called mimicry attacks. And then you get a different PDF file. And the problem is the original PDF file was classified as malicious, and it's still malicious, but it's now classified by whatever classifier you use as benign. Okay? So this example is an example of a much broader class of problems in security, which are problems about detection. You're trying to detect bad stuff. This example was an example of detecting PDF malware or malware in general, for example. You can have intrusion detection systems that are detecting intrusions. You can have spam detection and phishing email detection and so on. There's a very fundamental problem in security. It's the problem of detection. It's fairly natural to use machine learning for this problem. So how does this work in security? You have a collection of malicious files as well as a benign files. You have the collection labeled somehow. Then you extract features and get labels for those. That comprises your training data, x, y, right? And then you learn some function of x, which is successfully able to identify, at least in most instances, whether a particular file that's new, that's extracting features x, that's malicious or benign, okay? Now, in this generic framework, the way evasion attacks work is like this. You have an initial PDF file that, again, is used as an input into this classifier f of x, right? And initially, at least, it's classified correctly as malicious, and then the attacker comes in, changes this PDF file somehow, it gets fed into the f of x, and that's classified as benign. Okay. And the core problem I'm going to be talking about today is ROBUSTNESS, which is to make sure that that cycle can't work most of the time. Now, you'll never be able to prevent it in all cases, but our goal is to minimize the number of instances where the adversary, in fact, can succeed and change something about the file relatively straightforwardly, such that it still delivers a malicious payload, but it's classified as benign. So you want it to still be classified as malicious. Now, mathematically speaking, what is ROBUSTNESS? Okay, and ROBUSTNESS is a term I'm using. It means actually multiple things in the literature. So just so you're familiar with how I'm using this term, right? I'm hoping some of you are familiar with what's called empirical risk minimization. Basically, in standard machine learning, you solve an optimization problem, which in a nutshell tries to minimize the number of errors you make on a training data set. Robust version of this, you're trying to still minimize the number of errors you make on a training data set, but you're now allowing the attacker via this function, that's how this works, via this function A, which transforms initial instances X into some adversarial instances, you still have a relatively low error even after such a transformation, which is done adversarially. Okay? Now, typically, this problem, the way I formulate it right now, is a little abstract, right? So how does the adversary actually do this? What capabilities they have? So commonly, it's distilled a little bit more simply into a minimax problem. The adversary is trying to maximize damage, where damage is simply measured by your loss function that you're using typically. This is original paper from NIPS 2007. This is still a little abstract because you're still allowing this set of possible transformations to be anything arbitrary. So what's typically actually done is you take this formulation and you, in fact, narrow the space of what the adversary can do with respect to a particular model. So this model is this LP bounded transformations. So the adversary can change up to epsilon within some LP norm the feature vectors of the original instances. And sort of the approaches that are called either robust learning or certified robustness and whatnot essentially have, all of them have this flavor. They're not necessarily literally this, but they all have this flavor. Okay? Now, I'm going to call these class of models feature space attacks models, right? So the reason I highlighted this stuff in red is I'm going to call this stuff in red as a particular attack model, right? It's sort of hopefully immediate that this is a model, not actual attacks, because actual attacks do something that's far more complicated, okay? So bear with me to see how this works, right? So this is what I call feature space attack models. They have a few characteristics. Typically, the way they work, right, the attacker starts with the initial feature vector corresponding to an initial malicious instance. They transform this to some other feature vector x prime, and they incur a cost for modifying it, where the cost is just going to be measured by some LP norm, whatever your favorite norm would be. Okay? Now, the attacker doesn't just want to do this. Their goal is to fool the classifier, which is typically measured with respect to some loss function and or something called the score function, essentially the score of the whatever the target class is. So you're trying to, let's say, one simple example is if y is the true class, you're trying to if you're trying to make mistakes of any kind, you're trying to minimize that score, or some variations of that theme. Okay, so one way you can think about this is the attacker trading off kind of the cost of making the manipulations and how much error they introduce or how much they minimize the score of the true class or something like that. Okay, now this does not capture all the possible models. This just gives you a sense of what these kinds of models do. And so let me distill the class of models that I'm going to call feature space models into two characteristics. The first one is that the attacker can make arbitrary changes to the features. Okay, and the second one is that the cost function is measured by the LP norm. Okay, the third part, where they're trying to deceive the classifier or cause it to make errors, is not really an assumption of the model. It's in fact what the adversary is trying to do. Okay, so the modeling aspects are those two things. And you can think of what I'm going to talk about next as essentially a critique, not in a negative sense, but looking at some depth about whether this particular model of the world of adversarial examples makes sense and when and why. Okay? So I'm going to frame this endeavor as follows. Suppose we learn ROBUSTNESS against this kind of attack, the feature space attack. The question is it robust against real attacks? And it's hopefully immediate real attacks are really not like this. So what are they? Okay, can I even quantify what those mean? So I'm going to look at this question in two domains. One is a little bit older domain in adversarial machine learning. It's the malware detection problem, and specifically I'll look into PDF malware detection. The second problem is what's gained enormous amount of popularity in the research community today, which is image classification. So let's start with PDF malware detection. Okay, so how does this work? Hopefully what I've already said is enough background. But basically you have this function f of x that predicts whether x, being the feature vector, right, is malicious or not. The way this actually works, and this is important if you think about real attacks, is that x does not correspond to malicious instances. X is the features extracted from that. The malicious instances are actually files. I'm going to call them E, right, which features x are extracted. And then you're trying to predict whether this is benign or malicious based on these extracted features. Okay, so the reason I make that distinction is because if you look at PDF files, right, they're complicated. Okay, and there's actually many ways you can extract features from them. So I'm not going to go through sort of all of the details of how it looks like, but I'm going to differentiate between two approaches, which is roughly consistent with the way that the literature defines features for those files. And the first one is in terms of content, which is here on the left, and you can think of content as essentially as where you extract features using regular expressions. You know, does it have this particular tag? Does it have a JavaScript tag? How many instances of a JavaScript tag does it have? And so on. Okay. Another one is to try to get more at the semantic level of construction of PDF files, which is called structure-based. You can essentially view PDF files as cross-references among objects inside the PDF files, and you can extract this tree-level structure once you cut the loops. And any path in this tree you can view as a feature, right? And it's based on the PDF file, actual PDF file structure. Okay, so those are the two classes of PDF malware detectors that are out there. content-based and structure-based. The particular instances I'll be dealing with for content-based is called PDF rate. It's not going to be actual PDF rate, but the open source Mimicus implementation of it, because actual PDF rate is not fully documented, it's only partially documented, and it's not openly available to the public to play with. And I'll have a couple of variants of PDF rate implementation I'll use. Don't worry about the details here so much. And also I'll look at two variants of structure-based PDF detection. The one is actually a precursor to the other one. The older one is called SL 2013, following the Cernish and Leskov paper in Oakland, or I forget, that paper I think in NDSS actually in 2013. And HIDUS is sort of a revised version of the same class of malware detectors. All right, so what is an evasion problem in this space? So the attacker's goal is hopefully self-evident. It's to modify PDF files in order to have them misclassified as benign. But that's not all the attacker cares about. Actually, they have a core constraint, which is that those files remain malicious. In other words, they still execute a malicious payload. This is a very complicated function if you think about it, right? It's not exactly clear what preserving malicious payload means. In fact, if we knew this, we would solve the problem of PDF malware detection. The whole reason we're using proxies like machine learning is because we don't understand this problem very well. Okay, so the space of sort of PDF files with the same malicious payload is not easy to characterize. But that is in fact what the attacker wants to accomplish. And that's a hard constraint. If it doesn't execute the malicious payload, it's completely useless as far as the attacker is concerned. And there are a few examples in the literature that try to accomplish this goal in an automated or semi-automated way. Okay, so I'll just give you one example that I'll actually study in depth here. It's by Shu et al. And NDSS. It's called EVADEML. It's an automated tool using genetic programming to essentially morph malicious PDF files into other malicious PDF files by changing things around. And essentially still try to evade a classifier that you throw at it. Ultimately, what it does is, at the end, for any file that it proposes, it confirms that malicious functionality is preserved using a sandbox. Okay, and you have to do this essentially because there's no real other way to verify truly that malicious functionality has been preserved. So the way I'm going to define conceptually realizable attacks, it's not actually easy to define them mathematically, so I'm not going to try. But conceptually, they're going to have three pieces. Yeah. Is this better?
Turn your head, it doesn't quite. So you're very loud here and very soft here. So you should be good here.
Okay. All right. So they have three pieces to them, right? The first thing is they modify the actual entity as opposed to modifying the features that you extract from this entity. So it's, in some sense, the features are irrelevant to the attacker, right? It's the entity that gets modified. You still produce a valid PDF file at the end. The second one is they have the actual malicious effect. Okay, meaning execute the malicious payload. And the third piece is that you want to avoid detection, right? That's the whole point of the attacker. They're trying to make it be classified as benign, even if it's initially classified as malicious. And so the way that I would reformulate the question now a little bit more precisely is, does ROBUSTNESS, based on the model, which is a feature space attack model, okay, does it still defend against realizable evasion attacks? So hopefully that's clear now. And I'm going to use an example realizable evasion attack, EVADEML, that I've mentioned already. There's a host of reasons why I use this sort of as a core first study. One of them being is, at least at face value, it seems like the most powerful one. All of the other ones make particular assumptions. For example, typically allow you only to add objects but not to remove them. EVADEML allows you to essentially explore the full space of modifications to PDF. Of course, that doesn't come free, it comes at a cost. But at least at prima facie, it seems like it's the most powerful tool out there that's automated. So a few words about evaluation. It's sort of the thing you would expect. The first metric we're going to use is robustness, which is simply 1 minus success rate of attack. Right? So the lower the success rate of attack, the higher robustness. So you want that number to be large if you're a defender. And the second one is going to be just standard area under the ROC curve. But this area under the ROC curve is going to be in non-adversarial data. So if the attacker doesn't do anything, you still want to perform fairly well. Essentially, that's what it's saying. We're going to be interested in both of those things. And robustness is kind of a fuzzy thing in the sense that in some domains, depending on construction of the feature space, it's not even clear you can get robustness of any kind. So you always need something to compare to make any claims about robustness, right? Is it even possible? And so we'll have a robust baseline, which is a defense designed specifically against this realizable attack, EVADEML. Okay? So how do we do this on the defensive level, right? So if we're given an attack model, we need a generic way to construct a defense. And it turns out something called adversarial training in the literature, or what I call iterative retraining, does the trick. It's really elegant because it's completely agnostic to both what classifiers you use, in a sense, and as well as what attack approach you're using, because all you're doing in each iteration is adding more attacks, whatever the model is you're using to generate attacks. Those get added to the training set, and you basically just retrain up until either some convergence criterion is satisfied or until you're ready to stop for whatever reason. Okay, so it's quite generic. Okay, and it works both in batch mode, and the first study is going to be in terms of using this in batch mode, as well as in stochastic gradient descent mode if you're using neural networks. Okay, so the first set of experiments is going to answer, if you will, present evidence to answer the first question, which is ROBUSTML really robust? Okay, and we'll look at both content-based detection and structure-based detection using EVADEML. Okay, so here's content-based detection results. Let's look on the left first. Okay, vertical axis is robustness, so higher is better for the defender. Okay, no surprise if you have no defense, meaning the original classifier, it's terrible. That's exactly what we would expect given the literature. Okay, if you're using real attack, in this case EVADEML, in this adversarial training loop, it's essentially 100%. It's 97, 98% or something like that. And if you're defending against using ROBUSTML approach, which is just adversarial training with a feature space attack, okay, you get 100%. So this tells you two things. One is, it is not obvious a priori that this would work, because the ROBUSTML approach assumes something about a model which is decidedly completely unlike real attacks. Okay, right? Real attacks try to constrain, try to preserve malicious payload, which has, at face value, nothing to do with LP bounds on how many features you can modify, right? So it is not at all obvious that it would work, but it does in this domain. So it's 100%. But it's not free, okay? If you look on the right here, this is your sort of RUG curve representation. This is cut off at low false positive rates, because if false positive rates are relatively high, it's completely useless anyway. So this is kind of the range of application you actually care about. And you can see, so this heavy red line corresponds to the RUG curve for the feature space defense, and you lose a fair bit in this range, which you care about. So it comes at a cost. You get robustness, just like using real attack, but you pay for it. And this is also with if you binarize the features, you get something very similar. I'm not going to show you the plots, but essentially the same conclusion obtains here. That's content-based detection. What about structure-based detection? In structure-based detection, things are a little bit less optimistic, but still not as terrible as you would perhaps think at first. Again, no defense is terrible, no surprise there. Using real attack is essentially 100%, no surprise there either, right? You're doing adversarial training against the EVADEML itself. Okay. ROBUSTML is much better than doing nothing, right? But is significantly worse than defending against the EVADEML directly. So there's a gap, okay? And as well, also, this AUC is going to suffer a bit. So we have two issues that we've observed, right? One is that in some cases, at least, you do lose a substantial amount in robustness using these feature space models, but not always. And in many cases, fairly typically, in fact, you lose a lot in terms of baseline performance, not adversarial performance, which is just as important.
Could you remind me what is evasion robustness?
So 1 minus attack success rate. So the more successful, the higher fraction of instances the attacker succeeds in evading the classifier for, the lower robustness is. Yeah?
Was the using real attack one, was that the iterative retraining and ROBUSTML? So to keep apples to apples comparison, everything is adversarial training or iterative retraining. The only difference is which model you use in the loop, right? In the what I call using real attack, the model that generates adversarial instances is literally EVADEML,
when I'm calling ROBUSTNESS, the model that generates adversarial instances is a particular member of the feature space modeling class.
So, just to understand, so ROBUSTNESS is basically using a superset of the set of examples. Because real attack is more constrained, and ROBUSTNESS is not constrained. Is that a fair way to think about it?
It's not exactly more or less. Although you could argue it's less constrained. It's possible it's possible that preserving a malicious payload allows you to have much greater modifications in some cases to the features. It's also possible that allows you for some other features, for example, you can modify them by a lot less. So it's just orthogonal. Yeah, exactly. It's just orthogonal, basically. It's just something else entirely. Yeah.
How do you decide how big to make the LP norm ball for the ROBUSTNESS?
So we actually don't decide this. This is why we favor this trade-off formulation. So what we actually decide is how much you care about the cost versus, and we vary the cost. As you increase the cost, and the adversarial accuracy drops. If you increase it enough, it becomes completely useless. So this gives you kind of a sense of where you should set that relative trade-off. So we tried actually several variations. This is a reasonable summary of the results. That's actually the most optimistic. Yeah.
What P norm P equals to?
Because in 3 or 4 cases they're binary features, it doesn't actually matter. But we used, I think L2, but it's either L1 or L2. To be honest with you, I don't exactly remember now. But we can talk offline, or you can look at the paper. We say it on the paper. I just don't remember off the top of my head. Because in most cases, it actually doesn't matter for binary features. Okay, anyway, so how can we fix this? The idea, conceptually, is, feature space attacks, they seem to work partly, but they're entirely, disembodied from the domain of application, right? They're too abstract. And so we'd like to anchor them somehow in the actual domain that we care about, in the problem domain. And how do we do this? The idea is to do this heuristically by using a concept of conserved features. Now, it's key to understand that this is going to be heuristic. There's all kinds of ways you can defeat conserved features. And I'll show you how you can do this. But the idea is as follows. Essentially, we can identify features such that the only way to remove the feature corresponds to removing malicious functionality. This is just doing myopically, right? One feature at a time, okay? And it's heuristic because there's other ways to defeat this process from an adversary's perspective. But it does tie it into the particular problem we're trying to solve, which is malware detection, right? And the core constraint malicious instances face, which is preserving malicious payload, okay? And so we're going to ask, so first of all, we identify some of those features. There's a very small proportion of the features that we actually use, okay? We're going to ask 3 questions about these kinds of things, okay? So the first question is, for a machine learning person, the obvious question, right? So we know all kinds of ways to do sparse learning and regularization. In particular, one way we can identify features of this kind is by doing very sparse learning and figuring out what are sort of the small set of features that are most predictive of whether it's malicious or benign. And the question is this related to what we define as conserved features? The second question is the classifier that only uses conserved features still robust? I'm going to mostly skip that discussion because it's not so important. And the third question is, how can we use conserved features as a part of the ROBUSTNESS framework, and does it work? Okay, so let's get into it. So the first question is, what if we use L1 regularization, which allows you to get the sparse set of features? And this is evasion robustness on the vertical axis, right? So if you're using just 8 conserved features versus just the L1 regularized features, you can see that they're not really capturing a whole lot of value from these conserved features. This, by the way, sort of the second question just alludes to the fact that they're actually telling you the right thing. It's giving you some signal about what's relevant for the adversary to preserve malicious payload, with all the caveats aside. Okay. Now you can't sort of almost obviously can't just use the conserved features. If anything, if you look at just this RUC curve and only use conserved features, this is the curve right here, it's pretty terrible.
Can you say a little bit more about conserved features? So, like at a high level, what do you mean those two represent?
I'll give an example which maybe help, right? So for something like JavaScript tags, right? So JavaScript tags tend to be conserved because if you have a PDF file that fires up malicious payloads using JavaScript, and then you remove JavaScript objects, the malicious payload will go away. Okay, but there's also other things. For example, PDF has other sort of structural objects that break PDF readers if you don't have them, and those will also be conserved because once you remove them, it won't open and therefore won't run the malicious payload.
So I guess the conserved features essentially can't be manipulated, right?
So they can, but it's harder to manipulate them. But they can in fact be manipulated. That adversaries can be pretty clever, and when we play the adversaries, we can also be pretty clever. So I'll have a separate discussion about this very point. But for now, all I'm going to communicate is that this is a fairly heuristic way of doing it, but it does give you a signal in terms of something that the adversary cares about. And this is what I'm going to argue or demonstrate, is that that's actually ultimately sufficient for our purposes. All right, so first of all, how do I use it? It is actually fairly easy to use them. You just simply, by definition of conserved features, you just don't allow the adversary in feature space model to modify those features. There's only like 8 of them out of 6,001 case, so this has very little impact, right, in terms of what power the adversary actually has in feature space. But it does make a meaningful modification to the model. Okay, and so how do we do? The cases where we had done well before, it doesn't hurt, okay? But what about HIDOST, which is similar to SL 2013 in terms of results? Before we had a gap, if you remember, in terms of robustness, and now we don't. Okay, now it's 100% robust if you just use this feature space model by accounting for conserved features. Okay. The other thing that happens is that if you remember, the other issue was the RUG curves gave you some fairly bad results in terms of AUC. Mostly that now goes away as well. This is actually an easier one to understand because, right, we're allowing the adversary to modify fewer features. This essentially allows them to pollute the training data set a lot less. Okay? But in any case, so we do win on both of those scores. And I'm just going to claim that you can see the same results across the board for all of the settings we studied. And if you're interested, you're welcome to read the paper. Okay, so, but I'm going to move on. So if you're a security person, you would now probably stand up, okay, or sit down and just like raise your hand. I've had that happen, and say like, this is meaningless, or you have just one attack. This may be a very special attack. You know, what if you use another attack? Maybe all of this is broken. And the answer is, let's see, right? So let's look at other attacks and what happens, right? So now what we're going to do, we're going to actually ask 2 questions, okay? The first question is, so I have, as a defender, a couple of options. One is I have EVADEML, which I've argued is a pretty credible attack model. So I can try to run adversarial training with EVADEML, and that's my defense, right? It's a defense against a real attack, and so this is a fairly security way of doing business, right? I'm defending against something real, and I'm going to hope that it generalizes to other attacks, okay, by sort of an argument, but I don't know. The second question is we have a different way to defend it, which is this abstract model, feature space model with conserved features. And the question is the first case where you harden it with against evade effective against other attacks? And the second question is the same question, but with feature space models. Is it effective against other attacks? So I'm going to solicit intuition. What do you guys think is the answer going to be? You have 4 options, right? 2 for each. What do you think you're going to see?
No and yes.
No and yes. Okay, why? Because I wouldn't be giving this talk otherwise.
It seems, unless like, so I don't know the details about EVADEML, but unless it's some kind of weird super attack, it seems unlikely that a defense tailored for it would be usable against others.
That's fair, but I've sort of argued intuitively that it's kind of a weird super attack, right? You can make arbitrary modifications to PDFs, and it's exploring it using genetic programming. So the answer is no and yes. Okay, let's take a look. And we tried bunch of different attacks against it. So this is mimicry. I call it mimicry plus. It takes the original paper in Oakland from 2013 by Sir Eugene Laskov that runs a mimicry attack against malware classifiers. We basically just improve it. I'm not going to get into details how we improved it, but empirically it does work much better. Okay, and so the left this is just evasion robustness. On the left, it's hardened against EVADEML. It sucks, right? On the right is using ROBUSTNESS, and it's still good. Okay. Another attack is it's a reverse mimicry attack. The reverse mimicry attack does something like this. You have a collection of benign instances. You have a collection of malicious instances. You take a malicious instance, and essentially you pick a benign instance and you plop the malicious object into the benign instance. Right? So this makes the benign instance malicious. Okay, and again, it's very similar results. On the left is PDF rate, on the right is HIDOST. Pretty much the same conclusion as before. Okay, EVADEML defense works a little bit better, but still much worse than ROBUSTNESS. Now here, if you look a little bit more deeply about what's going on, it's actually kind of interesting. So why is it interesting? If we just look at a classifier that using conserved features, remember it was 100% robust against EVADEML, right? Now it's not 100% robust. Okay, and if you've been paying attention, that's meaningful because it means that somehow the attack is able to evade conserved features. So how is it doing that? Well, what it's doing is this. This is a structure-based PDF malware. The way that structure-based PDF malware detectors work is as follows. Okay, there's a sort of dirty little secret, right? So what you do is you look at sort of the whole set of structure paths you've ever seen. You take a relatively small subset of them. Still not very small, like 1,000 to 6,000, okay, of the most common ones. And those are your features. What do you do with the rest of them that occur? You throw them out. You ignore them. Okay? So what if the attacker constructs an entirely new structure path that eventually, through some sequence of hops, gets you to the JavaScript object that is completely invisible to the classifier? Okay? It's also why it's important to sort of think beyond the features themselves and into what's actually going on. So that's how it's actually defeating conserved features. Okay? And so this makes it kind of even more interesting, I would argue, the fact that nevertheless it's not defeating ROBUSTNESS. So there's a gestalt effect going on here that is not just captured by conserved features. Okay? Malgan is a generative adversarial networks for attacking stuff, and again, very similar observation here. Here was a fun experiment. So Mimicus implementation of PDF rate actually has a bug. It's a feature extraction bug. It doesn't account for sort of the updates to PDF specification that allows you to use hexadecimal NC code to specify tags. So essentially what the attacker can do is replace every tag with its hex representation. Since it's not in the feature space, it doesn't get caught by it's irrelevant to the reader because readers understand it, but it doesn't get caught by the feature extractor in this particular case. Again, the interesting thing is, of course, this defeats completely the conserved features because we're just representing them in hexadecimal. Okay, but this feature space attack model still works. ROBUSTNESS, if you will, still works. Okay, let's see how I'm doing on time. Alrighty. Okay, so just to sum up before I move on to the next part of the talk, right? So ROBUSTNESS seems to have nothing to do with real attacks on real evasion attacks on PDF malware detectors. So it's rather remarkable that they're actually fairly effective. Now, even though we still identified some limitations, we're essentially able to bridge them across the board by a minimal anchoring, if you will, to the actual problem domain. And it then exhibits a fairly generalized robustness to a host of other attacks. Now, for a lot of people, malware detection, as important as that may be, is kind of boring, okay? Because we like to look at pictures, and we like to see cars crash. Okay, maybe not like to see cars crash, right? But it's fun to see examples of attacks that cause cars to crash. We're not going to see any of those examples here, okay? But we'll see a lot of pictures. So I'm going to ask a few questions about the image classification domain. First of all, I need to frame it in the way that I framed everything else, right? So feature space attack misclassification is what everybody's talking about. So this is hopefully self-evident, right? It's the same LP norm constraint stuff. Okay, but what are realizable attacks? Okay, what does it even mean here? So let's go back to my conceptual characterization of what those are. There are three pieces to realizable attacks. One is they modify the actual entity, which is what, right? So we'll see. The second one is they have actual malicious effect, and the third one is they avoid detection. Okay, so what does it mean to modify the actual entity? That's what's called physical attacks, or physically realizable attacks in the literature. Okay, so for example, physical attacks on a stop sign actually place stickers on actual stop signs, okay, that look like graffiti. This is what you see over here. Okay, there's another really interesting attack on face recognition, where people put actual adversarial eyeglasses that defeat face recognition. That's on the right. Those are physical attacks, or realizable attacks in this domain. Okay, what about having actual malicious effect? Well, that's self-evident. Just causing the classifier to err is an actual malicious effect in this domain. Okay, what about avoiding detection? So this one is actually fairly contentious. It's not obvious what does it mean. Typically, people talk about notions of suspiciousness. And there's many ways to quantify suspiciousness. One is limiting LP norm, as people talk about. But actually, if you look at physically realizable attacks, that's not what they do. They're arguing essentially from the perspective of unsuspicious to people because it doesn't look particularly out of the ordinary, out of the domain of things that they typically see. So I'm going to ask a very similar set of questions that I asked before. The first question being, we have a set of ROBUSTNESS approaches to defeat these pixel-level digital attacks. Do those actually work to defend against physical attacks? Okay. So let's take a look. So I'm actually going to look at two sort of state-of-the-art ROBUSTNESS methods. One is using adversarial training, flavor of adversarial training that was designed by Madry et al. From ICLR 2018 paper, where the attack is a PGD attack. Actually, there's different variants of PGD, but we use the L-infinity variant. Another one that's very recent work, it's called randomized smoothing. It's got two pieces. One is at training time, you add Gaussian noise to instances, and then at test time, you add Gaussian noise. And this induces a probability for each class that it predicts that class. And you pick the class that has this highest induced probability, essentially. So this has been shown to work pretty well. Actually, both of those have been shown to work fairly well for whatever goals that they have in some sets of applications. And so I'm going to ask the question, do these methods work in defending against physical attacks? Okay. Now let's take a look. So here are some results for face recognition. Okay. Accuracy, including robust accuracy, is on the vertical axis. This is the percentage of instances that the defender gets right. Okay, the vertical axis essentially is the horizontal axis is the attacker's strength. Okay, so as you go to the right, you increase the number of iterations the attacker can run, optimize the attack. Okay, and in a nutshell, if you look at the plots carefully, right, so the baseline, which is the clean model or original model, is in heavy red on both cases. And then all of the other ones are sort of different variants. On the left of adversarial training with PGD, on the right of randomized smoothing. And I would argue that it's pretty clear it doesn't work very well. Okay. Okay, so what about traffic sign classification? Here things are somewhat better, right? Again, this is attacker strength, attack iterations. This is accuracy on the vertical axis. It works a bit better, but there's still a pretty significant drop-off. This is adversarial training, this is randomized smoothing, okay, for different parameters of these things. Okay?
I'm not sure I understood what attack iterations means.
Because I haven't explained it, but basically attacker is solving some complicated, some nonlinear, non-convex optimization problem, so all attacks are sort of iterative. And attack iteration you can view, if you will, as a form of capability or strength of the attacker. So the longer they let the optimization process to run, the better solutions they'll get. Of course, that sort of the added value is going to diminish as you get more iterations. So each of those is sort of iterative. You can actually, a lot of the times attacks are called learning as well. You're essentially sort of iteratively optimizing the attack. So anyway, here it's not great. It's a bit better than before. It's not great, but it's actually in a sense worse than you think, because this data is restricted just to classifying stop signs as stop signs or not. So this is why you see like 100% accuracy for a clean model. It's because this is a very simple task. And they still get it wrong quite a bit. Okay. Okay, so now what? So sort of state-of-the-art approaches don't work. So what can we do? And don't work particularly well. I would argue this suggests that the LP norm model in the image classification domain is somehow fundamentally flawed. Okay, and it's just an empirical claim now, right? I mean, before it was also fundamentally flawed, but it works with a minor tweak. Here it's fundamentally flawed and it also doesn't work, so that's bad, okay? And so the question is there a better model that captures these kinds of attacks? Now there's many ways you can implement physical attacks. I'm not gonna worry about all possible ways. I'm gonna worry about the masking or occlusion attacks, right? So these attacks have one thing in common, which is there's some stuff that occludes a part of the object you're trying to classify. Okay? And I'm going to leverage that piece of information to come up with a generic abstract attack. And this generic abstract attack I call rectangular occlusion attacks, and it's exactly what you would think it would be, right? First, you find a place for a rectangle, which you've specified somehow exogenously. You just place it adversarially in some place in an image, and then you engineer a very high magnitude adversarial noise inside the rectangle. Okay? Pictures are worth 1,000 words, as they say, right? So here's a picture of A.J. Buckley image. Okay, here's the rectangular occlusion attack in practice. Okay, it is not meant to be unsuspicious. It's quite suspicious. That's not the point. It's an abstract model that tries to capture kind of the variety of things you see. And this would cause it to get misclassified, which is the goal of this attack. How do we defend against this? So the defending actually is just you can run adversarial training against this ROA attack. I'm going to call this DOA, defense against adversarial occlusions. Okay. And so the question is, does it work? Okay, let's see how I'm doing it. Good. And the answer is yes, basically, right? So here's a plot. Accuracy on the vertical axis, again, attacker strength on the horizontal axis here. This is adversarial, so here, adversarial training for the best robust parameterization that you've seen. This is the best version of randomized smoothing in this particular domain. Here are two variants of DOA. Don't worry about what the variants mean. Okay, one is a bit more heuristic than the other. So this is hence state-of-the-art points here, right? In our approach are the lines that are fairly robust. This is for adversarial glasses attack. Actually, one side note, right? So you also worry about baseline effectiveness. That's actually pretty good, right? So if you see the point over here for both of those things at the extreme, that's actually pretty much the same as original effectiveness. And here's the results for the traffic sign classification, right? Again, sort of, this is the original model in red. The green and the blue are the variants of adversarial training and randomized smoothing. You'll notice these are a little different because the best variants are a little different in this domain. Okay, here is the DOA, and it's still considerably better in this domain. This is...
So is it, again, sort of going back to my original question, is it the case that the DOA basically you're blocking like a rectangular patch and training against that? So in a sense you're training against a much more intense distortion. And
So,
therefore succeeding against.
so it's actually not much. It's not a stronger attack. Okay. One other thing I can show you is that defending against ROA does not help you defend against the LP norm bounded attacks. So it's actually weaker. So it's really just different. Okay. It's meant to be just much more similar in structure to the kinds of physical occlusion attacks you tend to see. That's really it. But it's not stronger or really not stronger or weaker than the other attack. It's just different. Right, so here's, I don't know if you've seen adversarial patch attacks. These are patches you can place on essentially any object, and then it gets classified as some other target class or just as anything. And here too, I mean, sort of the black highlights the best performing models. What's not as clear is if you notice the comparison, it's kind of dramatically better. Right, and don't worry about sort of which of the final two is better. Those are both variants of DOA, and they're not actually all that different between them. And again, fairly minimal loss of baseline accuracy. Actually, no loss in this case. Okay, so a few takeaways, maybe bolder than I really mean them a bit, but you know, models are critical to science. So one of the fundamental questions in science of adversarial machine learning is what are the right models for the different domains you care about. The question is, so how do you know? How do you know that a particular model makes sense or not? There's various ways you can argue for it, but I would argue that intuition, which is a typical argument, is wrong. It's the wrong reason to say that model is right. And it's wrong for a couple of reasons, right? A lot of the times, natural models, okay, are not very good as an image classification. It seems like this digital perturbations model, which is pretty standard, it seems quite natural for the image classification task, and it does really badly. And then models that seem obviously completely unrelated to the actual attacks can actually work pretty well in practice. So ultimately, I'm kind of arguing here, you saw no theory in this talk, okay, at least not proofs of things, no theorems. Okay, I would argue it's still theory in the conceptual sense, but there's no theorems and proofs, okay? Because ultimately, the right answer at the end of the day is whether the experiments demonstrate that whether it works or not, a particular model makes sense or not, okay? And so I want to just sort of highlight kind of the bigger issue when it comes to science of security, right? Because a lot of the times, one of the things you see is that if you look at whether model is a good representation of the original attacks, I'm arguing that's not actually the right question, even though it's very similar to the kinds of scientific questions you would want to ask. What really matters in security is whether the defense based on the model actually works. And that's the kind of the core scientific question that you want to ask. Thanks.
Is it really fair to compare these three experiments? Because actually I think like the Madry's paper and also Cohen's paper, they are like trying to use a type that is visually deceptive. So
sorry, they're trying to do what?
like their experiments like trying to see like very small change that actually human eyes cannot distinguish. But like you say like you change the picture region of it and it seems like visually you can catch it. Right?
So it depends on what you mean by fair. I mean, the question, actually there's another paper that I don't know if it's ever been published, but it's an archive, essentially with the title like, what's the correct threat model, right? What is not clear to me and some other people in literature is that what, as a security problem, right, what problem is that paper trying to solve? Right, so I understand the problem there, it has a mathematical formulation. What is not clear is that what problem in the end is it trying to solve, right? What is the security problem there? Let me just sort of give you intuition why this is not obvious. If the attacker, in fact, if you say that the attacker in fact can manipulate pixels directly, then you're host, right? Because the attacker will just replace the image with something, right? So that's not the threat model that they have in mind. And so there's sort of a longer discussion, right? The original papers on these adversarial did not have security in mind. They basically were like, here's what here are some examples we found. Like this looks weird. Here you go, right? They didn't have a security motivation, right? What I'm simply saying is that if you take the security motivation seriously, then you start thinking, so what is the threat model? I presented one threat model, right, where the attacker modifies, you can think of it as physical hacking. They modify some physical objects that cause the AI system to err, right? That's a credible threat model. It's clearly fairly easy for attackers to do this. They can be unsuspicious. And then the question is, so what can you do to defend it? So the first answer is, we can apply state-of-the-art approaches, right, like Madry et al. And they just don't work, right? So I would argue it's not that it's an unfair comparison, right? It's a comparison to what you would do without anything else, right? There's no other thing to compare it to.
Basically, you mean you have to know what kind of attack you can design your experiments.
So at the end of the day, right, threat model is critical to security research, right? So what is it that you're trying to prevent, right? What bad things from happening? What attackers can do to you, right? What are their capabilities, information, and so forth. So that goes into what attacks you're going to evaluate on, right? I absolutely cannot claim this works for all attacks. It doesn't. I can prove to you it doesn't fairly easily. It's a class of attacks that I'm claiming that this is helpful for. Okay, these attacks have these sort of occlusion properties. This is not meant to replace all other research, right? There's other motivations potentially for the other things that people do. And as a matter of fact, right, even though, right, the sort of the baseline threat models sort of defending against LP norm bounded attacks doesn't seem to work, our threat model is still informed by this research, right? Because we're still ultimately using, inside the rectangle, we're using PGD to try to generate these high magnitude adversarial examples, right? So all of this stuff is useful, but I think that, at the end, what we need to start being much more explicit about is, first of all, what are the models and what you actually care about, and which models make sense for which domain, right, and why.
So you made this comment that it's important to look beyond the features to see what's happening underneath. And that makes me wonder, so I'm not a machine learning person, I'm a programming languages person, and your PDF examples made me think, like, okay, maybe there's some kind of lightweight static analysis that gives your machine learning system like more information that it needs to defeat these attacks. So I was wondering, like, this anchoring to the problem domain, have you considered doing that anchoring by non-machine learning techniques, and would that be useful to this line of work?
Oh, good. So actually, our anchoring is not machine learning. So we actually use the sandbox directly to identify conserved features. Per your question, actually, I mean, you can think of all malware detection and feature extraction part of it specifically as essentially some form of lightweight static analysis, right? So typically, this is done because you can do more things. Like sandbox themselves are actually, if you will, a form of detection. They're just dynamic and extremely expensive to run.
Right. I think at this point it's past 1, so if you have further questions, perhaps we could approach